All right. So we got just a little bit to finish up in 7.2, okay, and then the rest of the time we'll just work on Hawks. So if you don't want Hawks help, you're free to go after we get done doing the little lecture part. Okay. If you don't want Hawks help, hang around. Okay, we'll stay the rest of the time and I'll help. Okay. Anybody have any questions or anything we need to talk about before we finish up on the little lecture thing? None of the 7.2. Well, so a little bit of it we got going, but we still got to finish it up. So, yeah. Okay. Still got a couple things we're missing. So. Okay. Think anything else? Okay, we don't have much left. We don't have much left. So, last time we ended off looking at factorial expressions, how to work with those. One reason why we're working with these. Okay. One reason why we're working with the factorials is because we're going to need them, okay, to do a couple of other calculations. Okay. Okay. So we got these two, we can call them counting techniques. Okay, we have left to do. One's called combinations. All right, give me just a second. Okay. And this one's called combinations. So we're gonna have a formula for it in a second. Okay. But we need to talk about when to use the combinations idea. Okay. So the idea is that we have a group of objects and we're trying to choose some number of objects out of the group. Okay, so maybe we have 20 objects and we want to figure out how many ways we could pick 5 of those things, okay, out of the 20. Okay. So to do that, we could use combinations, and the idea here with combinations is that the order is not important. It doesn't matter which order we choose them. Okay. That's when we use combinations. The other one, same idea. Okay, so if you're missing some of the verbiage here, we're okay. On the other one, we're dealing with permutations. Okay, so we're still choosing a number of objects from a group of objects. But the difference between the two is that with permutations, the order does matter. Okay, the order is important. We're not going to have a lot of these because it can get a little tricky sometimes being confident, okay, whether or not the order matters. So we've got a couple in the assignment, but they're pretty clear on whether or not the order matters. But most of the problems in the 7.2 assignment you can do just using that fundamental counting principle where you just multiply the numbers of choices for each thing together. We'll have a few combinations of permutations, not many. So let's look at a couple of scenarios and pick out which one we should use: combinations where the order does not matter, or permutations where the order does matter. Okay. So let's look at this first one. Okay, so A says, in how many ways can first, second, and third place prizes be handed out to science fair winners if there are 30 students participating? Okay. So is winning first place the same thing as winning third place? No, it's not different, right? So the prizes are probably even different. Okay, so here the order matters, right? It matters if you win first or if you win third. So since the order would matter on this one, we would use permutations to figure that number out. Okay. Because our 3 spots we're picking, order matters here. Not on this one. We're about to do some. Yeah, we haven't got the formula yet, so we would use permutations on that one. I think let's look at this one. It says each department needs 2 student representatives from each major on the campus committee. How many ways can the biology department choose the representatives from the 45 students who are majoring in biology? So we've got 45 students majoring in biology. We want to pick 2 of them. Does it matter if you're the first person they pick or the second person they pick? No, because you're on the committee either way, and there's no difference. There's not like a ranking or anything. Okay, so since the order doesn't matter on this one, we would use combinations. That's the idea behind sometimes the order matters, sometimes it doesn't. All right, so if we can figure that part out, we're ready to take a look at the formulas. Okay, not bad. They use factorial, so they look a little scary, but they're really not bad. Okay, so if we want to calculate combinations, this thing down at the bottom is what we get. Okay, so we really just have 2 numbers coming into play. One we're calling R, one we're calling N. It's important that you know which one's which, okay? Because if you get them mixed up, you will get the wrong number. So we are choosing R objects out of a total of N. So R is how many we're picking, N is the total we had to choose from. If that's the case, there's some notation that goes along with it, but we really don't care in here, okay? We just take our total number factorial over our choosing number factorial times the total minus the choosing number factorial. That's combinations. All right. And permutations, the formula is similar, but it's actually a little bit simpler. Okay? So with permutations, we're still same R and N. We're still choosing R things out of N possibilities. We just have one less term in the permutations formula, so we don't have the R factorial part in permutations. Not bad. As long as you remember what factorial means, we're in pretty good shape on these. So let's do a few. We don't have many. Okay, well, I think I've got 3 maybe. So let's do some permutations and combinations, and then that'll be it for this section. Okay. So let's look at this first one here. This one's referring back to some sandwich example that we didn't see, so don't worry about that. But the part that we care, it says suppose there are 18 toppings put on our sandwich, okay, after we've picked bread, meat, and cheese. How many different possible sandwiches would there be if we could choose 4 toppings? Okay. So here we've got 18 things to choose from. We're trying to choose 4 of them. Okay, so we have to think about, does the order we choose the toppings matter? Okay. No, it doesn't. So, okay, to you personally, you might care if you put like tomato on or lettuce on first, okay? But as far as what type of sandwich it is, it doesn't make a difference. And so order does not matter here, so we'll use combinations. Okay, so our formula for combinations is this. Okay. Now remember, N is our total, so 18, that's N. R is how many things we're choosing, so R is 4. So then we can just plug into our formula here, and then we simplify. So we've got 18 factorial over 4 factorial times, 1 second, I got something on my screen up here. Okay, 18 factorial over 4 factorial times 18 minus 4 factorial. So if we do the subtraction, that turns into 14 factorial. And remember our little trick with the cancellations, right? So the factorial, 18 factorial means 18 times 17 times 16 times 15, all the way down to 1. On the bottom, this 14 factorial, we would have 14 times 13 times 12 times 11 times 10, all the way down to 1. So remember that trick we had with the cancellations, everything from 14 down to 1 is going to cancel. Okay? So on the top, that'll leave us 18 times 17 times 16 times 15. The 14 and down will cancel with the 14 factorial on the bottom. But then we still have 4 factorial in the bottom. That part we can figure out. That gives us 3,060 different sandwiches. So if we've got 18 toppings, how many different ways can we choose 4 of those toppings? Got 3,060 different ways to do that. Those numbers always seem too big to me. Yep. So I did. Yeah, I did. Exactly that. So you could, if you want to put it in all at one time, you can put parentheses around top and around the bottom. What did I divide by? All right, so I did what I did in my calculator. I did 18 times 17 times 16 times 15, hit equal, and then divided by, and then I put parentheses 4 times 3 times 2 times 1. So we're dividing by 24. Right, we end up dividing by. Good question. Anybody else have something? Any of those? You could potentially do it with the factorial button in the calculator too. Not much faster. Okay. Let's look at another one. Let's look at this one. So it says, consider a race with 140 participants. How many possible outcomes are there for the top 3 positions of gold, silver, and bronze? Okay, so winning gold's not the same as winning bronze. So here order matters. So we would do permutations. Permutations formula is this, n factorial over n minus r factorial. Here we've got a total of 140 participants, that's our n. And we're choosing 3, so r is 3. So we'll have 140 factorial over 140 minus 3 factorial. So on the bottom, 140 minus 3, that gives us 137 factorial. These are gigantic numbers. But we can use our cancellation trick. So on top, we'll have 140 times 139 times 138 times 137, all the way down to 1. On the bottom, it starts at 137 down to 1, so everything 137 or smaller is going to cancel. On the top, we're just left with 140 times 139 times 138. And that number is also pretty big. So, see what we get there. I think I'm going to get scientific notation. No, okay, that number's not the bad one. Okay, so that one is 2,685,480. That one comes out to. A little bit mind-blowing if you stop and think about it. But we had 140 people. Questions on that one? You okay with how we do the cancellation? No, because the 137 cancels out with the 137, 136, 130, yeah. So we just have 1 on the bottom. We're done on that one. Other thoughts or questions? Okay, let's do one more. And this one will be helpful for the assignment for sure. Okay, this last one. It can be a little, you can just do it with the fundamental counting principle, but you can do it with permutations also. So this one says, how many possible ways are there to arrange the order of appearance for the contestants in the local talent show if there are 15 contestants altogether? So here, order does matter. And it's going first is not the same as going last. So we'll do permutations. We got 15 contestants to choose from, so that's n. This one's weird because how many of the 15 are we picking? We're picking all of them. Right? We're picking all of them. We're just picking the order. Right? So we're going to have 15 people that compete no matter what. So R is also 15 on this one. Well, it's weird. So we're saying if we've got 15 people, how many different orders could we choose all 15? And so we've got 15. We're picking 15. So we plug into our formula, we've got 15 factorial over the bottom's n minus r factorial, so 15 minus 15 factorial. So we've got 15 factorial over 0 factorial. You remember from last time what 0 factorial is? 1. So we really just want 15 factorial. And this is a really big number. A really big number. So let me give you this one. That number is 1,307,674,368,000 different ways we could choose 15 out of 15 people. That's astounding. Doesn't seem like it should be that big, but I'm saying how many different orders can we put 15 people in? And I said you could do it with the fundamental counting principle, right? So you would end up with the same thing, but doing the fundamental counting principle, you would think about how many choices do I have for the first person, 15. How many do I have for the next person? One's already gone, so the second spot you'd have 14 choices. Third spot you'd have 13 choices. So you'd end up with 15 factorial, doing the fundamental counting principle too. Gigantic number there. Questions on that one? The hard to believe is it makes you suspicious that it's that many. Like it's a huge number. There are really that many ways you could put 15 people in order. Yep. Okay. Remember, factorials grow really quickly. All right, so the first, 2 factorial, 3 factorial, they don't seem like a big deal. But by the time you get to 15, you're starting to get into huge numbers. All right. So that's it for the lecture. If you want to hang around and get Hawk's help, I'll be glad to do that. Okay, but if you're comfortable where you're at in Hawks, you don't have to hang around with us. It's just up to you. If you didn't get on the sign-in sheet, make sure you